Finding the ground truth, macrophage tracking in cancer research. Monoclonal antibody therapy has become a common treatment of many different diseases, such as various cancers including CLL and many autoimmune diseases. The major mechanism of MAB depletion of CLL cells during therapy is ADCP, which is a finite capacity mechanism where target cells can be lost when the system becomes overwhelmed. Since resistance to MAB therapy has been linked to the loss of ADCP activity, we propose that developing new tools to measure ADCP activity at higher resolution would help to improve our understanding of it and help us to determine how to prevent MAB therapy resistance. To capture the rapid dynamics of ADCP, the CHU Lab developed a microscopic imaging technique to visualize this process. However, as you can see from this video, it results in enormous amounts of image data consisting of approximately 100 macrophages imaged every 1.5 minutes for up to 12 hours. At this scale, analysis is daunting and requires tracking of hundreds of macrophages and thousands of tumor cells over hundreds of video frames. So our goal for this project was to develop an automatic program capable of tracking these events in place of manual analysis. However, first, we need to establish a ground truth to determine the accuracy of said program. With the help of Joshua Zent from Ohio State University, we used a Fiji-based program to manually outline the individual macrophages as shown in this image. Each cell was completed one at a time across all 206 frames before moving on to the next one using Seg2Track's manual selection. Students completed these outlines across hundreds of video frames, resulting in overlays like the one shown on the left. Zent's automatic program generated similar overlays as shown on the right. We then used these to collect more data and compare various parameters like integrated density or mean density of the automatic program to the manual student data, which served as our ground truth. This graph shows macrophages per frame as calculated by the students and the automatic program. As you can see, all students recorded the same number of macrophages across all 206 frames, as opposed to the automatic, which was constantly fluctuating. We'll talk more about the reasons for this in just a few minutes. Two of the students' data were identical, so they overlap, and one cannot be seen in this figure. We also compared various parameters of manually selected macrophages to those that were automatically generated. Graph A shows the mean density values, with the blue line indicating the automatic program, while graph B indicates total integrated density. Again, automatic program values tended to fluctuate more, but were not far off from student values. In fact, a one-way ANOVA showed no significant difference between the automatic and student data when related to integrated density. This means that the overall areas selected were likely very similar, even though the individual or automatic macrophage selections may have been incorrect, as shown by the inconsistent number of macrophages per frame. The overlay shown here was also generated by the automatic program. It shows 9 macrophages identified, even though through our ground truth analysis, this video was determined to only have 6 macrophages that remain throughout the image's entirety. During analysis, we determined 2 different types of short-lived errors that seem to be occurring. Split cell errors, like cells 12 and 13 in this image, that show one macrophage being identified as 2 separate cells, or high exposure points that are often too small for us to notice, but are identified by the program as their own cell, like cells 7 and 23. These types of errors contribute to the incorrect number of macrophages per frame calculated by the automatic program. However, many of them only lasted for a few frames at a time, so we could potentially factor out most of these errors by implementing a minimum persistence length requirement to identify a cell as a macrophage. Some of our most important takeaways from this project were that the Seg2Track's program was easy to use for students and allowed for highly reproducible data collection that could be used as a ground truth in future research. Based on this ground truth data, the automatic program was shown to be somewhat successful in macrophage identification, but requires further development to account for the identified sources of error. By completing more trials, we hope to continue troubleshooting and improving this program for the future to hopefully study ADCP kinetics without the need for manual analysis.